The net electric field. Adding individual electric fields will give the electric field created by the presence of the multiple charges. There are some rules for drawing these. 1. Electric field lines begin on a positive charge and end on a negative charge. 2. The density of the electric field line's distribution is proportional to the size of the charges. 3. The lines never cross, or else there would be multiple values of electric force at the crossing point. And 4. The lines are continuous. These are the electric field configurations due to two like charges. There is no electric field midway between the charges. The individual electric field vectors cancel out. The shape of the field is the same for both positive and negative charges, only the field direction is different. For the positive charges, the field points away. For the negative charges, the electric field points towards. This is the electric dipole configuration, consisting of two unlike charges. There are no places where the electric field is zero. Again, the shape of the field is the same for both positive and negative charges, only the field direction is different. Whether the positive's on this side or this side, the picture looks the same, except the arrows go from positive to negative, so they're in different directions for the two configurations. Since the electric field is represented by vectors, the net electric field at a location due to multiple charges is calculated by adding each of the vectors together. N is a total number of fields acting on a location. The direction of each electric field determines the sign used when you're calculating the individual values. Let's work through a problem. We want to find the net electric field at the origin due to these three charges. So the first thing you'll do is draw the origin point on the drawing where the electric field is to be calculated. Here the origin is at x equals 0. Draw the electric field at the origin due to each charge. Determine the magnitude for E1, E2, and E3 at that position, and then add them together algebraically to find the net electric field at the origin. Here's our first step. Mark the origin point. Well, here it is, at x is equal to 0. Draw the electric field at the origin due to each charge. Each charge has an electric field. To find the electric fields acting at the origin, first draw the electric field around each charge and identify the direction of the field at the origin. So let's start with Q1. It has its electric field lines pointing in all directions, but we only care about where this line points at the origin, This electric field is going off there. That's not going to affect our origin. So this line is pointing to the right at the origin, and we show that right down here. How about E2? Same thing. Its electric field is pointing to the right. Even at the origin, it's pointing to the right. As a matter of fact, over here, it's still pointing to the right. We just don't care about that yet. The only different one is E3. You might think since they're all positive charges, they'll all point in the same direction. But Q3 is to the right of the origin, and its electric field is pointing to the left. So that shows up over here. Next, determine the magnitude of the three electric fields, which are represented here. That's their directions at the origin. So each one will be K times the magnitude of the charge divided by the distance away from the origin squared. Then finally, to find the net electric field at the origin, you take these magnitudes here and assign a sign to each one. If they're pointing to the right, like E1 and E2, they get a positive sign. E3 is pointing to the left, so that gets a negative. So you're adding a negative A3 or subtracting E3. Now let's work the problem numerically, but we're only going to have two charges, Q1 and Q2. So the first step, draw the electric fields acting at x equals 0. So we mark our origin, or x equals 0 there, and then the electric fields at that point are created by the two positive charges Q1 and Q2, and both point away from them. right? Because we're interested in finding the field here. Q1 electric field goes out like this. So at this point, it's to the right. Q2 is pointing its electric field to the left. So at this point, it will be in that direction, which is what we're showing right here. Next, find the magnitude and direction of the electric field at the origin due to the charge Q1, which has a magnitude of 9.1 microcoulombs. We start with our givens and convert microcoulombs to coulombs, where 1 microcoulomb is 10 to the minus 6 coulomb. We have our definition of electric field. We substitute in Coulomb's constant, the charge, and divide it by the distance away from the origin, which is 8. Make sure you square it. And we get 1.3 times 10 to the third newtons per coulomb. The electric field at the origin points away from Q1, so we're going to give that a positive sign later on. Now find the magnitude and direction of the electric field at the origin due to charge Q2, which has a magnitude of 3 microcoulombs. For the givens, we convert microcoulombs to coulombs, and then how far away are we from the origin from Q2? 3, so R is 3. Have our definition of electric field, substitute in our givens, and then come up with 3.0 times 10 to the third newtons per coulomb. Now, which way is that pointing due to Q2? Well, it's pointing to the left, so we're going to assign that a negative value. And finally, find the magnitude and direction of the net electric field at the origin. We've actually drawn E2 greater than E1 because that's what our calculations show. That's not terribly important. The most important thing is to get the direction right, because E1 we're giving a positive value because it's pointing to the right, and E2 has a negative value. So the total electric field is E1 plus E2. E1 is positive, E2 is negative, so you add them together and you get negative 1.7 times 10 to the third newtons per coulomb. That indicates that the net electric field is in the negative direction, which means it's pointing to the left.